Alright, so in this video, I'm gonna be explaining another important paper with the title Structural Node Embeddings in Graphs via Anonymous Walks. This I cleared paper in 2019. Graph embedding constitutes the challenging task of efficiently capturing the structural information of graph data in a lower dimensional space to be subsequently used as input for downstream tasks. We analyze the problem of network representation learning under a structural perspective. For example, to encapsulate in our node embeddings the local structure of the subgraph surrounding each node, which in practice is helpful to describe real-world network datasets without, the best tool for capturing structure around a node and also local and semi-local and global structure is one of these tools. Finding a subgraph around each node and then compare the graph kernel between these two to find similarity. So graph kernel is just one approach. Another approach that I used for my previous paper, graph structure attention network, you can read it in archive. I used anonymous random walk in order to generalize graph attention network. There are other approaches, but these two are very fundamental, especially for the local and semi-local and also for global structure of the graph, in the graph. So we propose and analyze an unsupervised embedding approach that builds upon anonymous walk statistics as a theoretically justified mechanism to encapsulate the structure of the graph. We successfully implement and benchmark our proposed model with state-of-the-art random walk-based model using well-known airline networks for node classification. So you want to have, this is the definition of how we calculate the anonymous random walks. So we have physical embeddings, we have structural embeddings. When we concatenate all of these, it becomes a richer feature than just physical embedding. That's why we need to add even positional encoding in graph transformer, in transformers, in GNN. This positional encoding is a kind of global structure, or sometimes in a different formulation, they pose it differently as a local modeling. It all tries to capture some structural thing beyond the physical attributes of each node. So the proposed graph embedding is like this. In contrast with this reference for modern graph embedding, we define a memory-efficient way to represent the anonymous walks. So we obtain this to encode a set of anonymous walks from node T. So starting from T, we have this anonymous walk, this is anonymous walk. So we have different walks, and we can have an attention over all these walks to see which one is more significant, having more contribution. And based on the theoretical guarantees, we propose a model that uses our anonymous walk representation, which captures local structure statistics and encodes those sets of walks using set2vec, which uses attention mechanism together with LSTM to find an order invariant representation. So this is a benchmark result with toy structured graphs.